Okay, so
Don't learn from past mistakes.
the start of this is the impulse momentum equation. Which says that if you take the integral of the net force with respect to time, that's equal to the change in momentum. So momentum at instant 2 minus the momentum at instant 1. So we're gonna just do this in the y direction. So in this problem, everything happens in the y direction. So this equation to us says that the y component of the net force integrated with respect to time is equal to P2 y component minus P1 y component. And we're going to assume, like we always do on these, that the net force is constant. It's not true. I mean, it's going to be changing, but if you're only calculating the average force, then the way to approach this is to treat it like that force is constant. So that says that you can pull f net y out of the integral because it's constant, and we're integrating over the time 0 to 0.2 dt. And that's equal to, so we have to figure out the two momentums. At instant 2, the momentum is the mass times the y velocity, which is 2.5. At instant 1, he's at rest, so it's 0. And we end up with 0.2 f net y is equal to 125. And so f net y is equal to 625. So now for part B, we're trying to go from this net force to the contact force. Usually with these problems, the impact happens fast enough that you can assume that the net force is the same as the contact force. The contact force is the only thing that matters. But if you're asked specifically for it, you can break it down into the net force being the sum of all the individual components. So we have 0, 6, no. So let's think of a free body diagram. There's the leaper. So the forces acting are the person's weight, 490.5, and the contact force, I'll call it R. And the net force is the sum of these individual forces. So 0, negative 490.5, plus 0R is equal to, that's just force of habit, is equal to the net force, 0, 625. And so you can just solve for R. You get that R is equal to, what was it, 1155? Okay. And so then if you're trying to find the force vector on the person by the ground, that's this. All you have to do is fill in the variable. So this is F on the person by the ground. So the force on the person by the ground is equal to 0.1115.5. So then for part C, we're trying to figure out the force on the ground by the person. Anytime you're talking about a contact force, and you're just trying to flip which one's acting on which, Newton's third law says the force on the ground by the person is equal to the negative force on the person by the ground. And so that's equal to negative 1115.5. And then the last one is just a kinematics problem. Just a free fall problem. So you can do it as 2ay times pfy minus p0y is equal to vfy squared minus v0y squared. AY is negative 9.81, so this is 19.62 negative, times PFY that we're trying to find, minus 0, is equal to, when the person reaches the highest point, the velocity is 0. And right as the person leaves the floor, right when the free fall starts, we know that that initial velocity is 2.5. So you get negative 19.62 PFY is equal to negative 6.25. So PFY is equal to, what do you get for that? 0.3 something? 0.31, call it 9 meters. Okay? Any questions about that? Okay, here's another problem. That was the impulse momentum equation. This next one has to do with conservation of momentum. So three objects in space are free to collide, and they have internal things going on, some kinds of motors or whatever. So we'll say they can also explode, whatever is happening. But there's no external forces on this system of three things. At time 1, the 1 kilogram object has a velocity vector that's equal to 30 meters per second. A 2 kilogram object has a velocity equal to -1, -5 meters per second. And a 3 kilogram object has a velocity equal to -2, 0. At time 2, the 1 kilogram object has a velocity equal to 0, -4. The 2 kilogram object has a velocity vector equal to -3, -8. And the question is, at time 2, what's the velocity of the 3 kilogram object? Okay? So you can erase that stuff and see if you can figure this one out. So for this one, the idea is conservation of momentum. Conservation of linear momentum. Which says M1 V1 plus M2 V2 plus M3 V3 before is equal to M1 V1 plus M2 V2 plus M3 V3 after. And so we have 3 times, what are the vectors? 3 times 3, 0. Oh, no. So the 1 kilogram is, the 1 kilogram object has a velocity of 3, 0 before. The 2 kilogram object has a velocity of -1, -5. And the 3 kilogram object has a velocity of -2, 0. And then at the later instant, the 1 kilogram object has a velocity of 0, -4. The 2 kilogram object has a velocity of -3, -8. And we're trying to figure out what the velocities of the 3 kilogram object are. So we get a first equation that says 3 minus 2 minus 6 is equal to -6 plus 3vx. And so Vx is equal to 1/3. And the second equation says -10 is equal to -4 minus 16 plus 3vy. So +10 is equal to 3vy. So vy is equal to 10/3. And so after the collision, or after, at this later instant, the velocity of the 3 kilogram object is 1/3, 10/3. So you can always use conservation of energy if you know everything about the velocities before and after of all but one object. That's not a super satisfying result. What you would like to be able to do is figure out if you know what the velocities of the objects are like before a collision, you'd like to know exactly what the velocities are after the collision. But the difficulty with that is that you know intuitively that that can't be the case, because I mentioned last time, what if you have two half-kilogram billiard balls that collide, and then with the same velocities before the collision, you have two half-kilogram bags of pudding. The collisions are not going to be the same. The velocities after aren't going to be the same. And it doesn't have to do with the momentums before. It has to do with the nature of the collision itself. So in order to be able to do more than find one single velocity before or after, like we did in this problem, we need to be able to specify something about the collision. So we need to go into collision types. And there are infinitely many collision types, so we can't cover them all, But we're going to cover sort of two extreme examples. So we're going to do inelastic collisions, which just means that after the collision, the objects stick together. And then we're going to talk about perfectly elastic collisions. And those are ones that bounce apart. And they bounce apart in such a way that a certain kind of energy stays the same. And we'll talk about that when we get to it. So out of all the collisions that happen in the universe, what percentage of them would you guess fall into these two categories? 0, right? But these are useful because a lot of collisions are close to these, and you can get reasonable results by treating them this way. So if you have two lumps of clay that collide, you'd assume that you treat it like it's going to be elastic, and that'll give you better results than not knowing anything about the collision. If two billiard balls collide, you're going to assume it's perfectly elastic. It wouldn't really be perfectly elastic. You lose some energy, but still that'll give you pretty good results. Okay, so the first one is inelastic collisions. So this is when objects stick together. And this is the easy one. Conceptually, one isn't harder than the other one, really, but there's just more math involved in inelastic collisions. Inelastic collisions, all you do is after the collision, you assume that they're going to have the same velocity because they stick together. Okay, so you can write this as conservation of linear momentum simplifies to m1 v1 plus m2 v2 plus however many you have before the collision is equal to, if they all have the same velocities, you can simplify this as m1 plus m2 plus however many you have times v after. So this is for inelastic. Inelastic collisions only. All right, so here's an example. So that's a skateboard. There's a kid standing on this skateboard. Okay, and a ball is thrown to this kid with a horizontal component of velocity of, let's say, 10 meters per second. The mass of the ball is 0.5 kilogram. And the mass of the kid is 20 kilograms. If the kid catches the ball, what's the velocity of the kid / ball after the catch? Well, remember, we're going to always take a top view for these problems. So from above, it looks like okay, so from above it looks like this. The ball's coming in at 10 meters per second. The kid's at rest before the collision. And we'll use a coordinate system like this. So conservation of linear momentum with the inelastic simplification says the mass of the ball times 10, 0, plus the mass of the kid times the kid's velocity before the collision is equal to 0.5 plus 20 times their velocities after the collision. And so you have one equation that says 0.5 times 10 is equal to 20.5 Vx, and a second equation that says 0 is equal to 20.5 Vy. So Vx is equal to, can someone divide that? What's 5 divided by 20.5?
0.24.
Okay, and the y component is 0. Any questions about that? Okay. You can also have them where they're not at rest before the collision. So if you have, let's say your first object is 1 kilogram and it's going this way before the collision, and your other one is half a kilogram, and it's going this way before the collision. Let's say that V1 is equal to 3 negative 4 meters per second, and V2 is equal to 2 meters per second. If the objects stick together, what's the velocity vector after the collision? So conservation of linear momentum for inelastic simplification says 1 times 3 negative 4 plus 0.5 times 2 is equal to 1 plus 0.5 times Vx Vy. And so the two equations say 4 is equal to 1.5 Vx. And the second equation says negative 3 is equal to 1.5 Vy. What's 4 divided by 1.5? 8/3. And then this one says Vy is equal to negative 2. So the velocity of the combined system after is 8/3 negative 2. Okay, the other type is elastic. In elastic collisions, the objects bounce apart without losing what's called kinetic energy. And so we have to define kinetic energy. That's going to be a big thing in this class in the next few sections. So the first thing we have to do is define kinetic energy. An object with a mass m and a speed capital V has kinetic energy 1/2 mv squared. If instead of knowing the speed, you know the velocity components, so if you know the velocity vector of the object rather than the speed, Then the kinetic energy is 1/2 times the mass times the x component of the velocity squared plus the y component of the velocity squared. So really all that's doing is using the fact that the speed is equal to the magnitude of that vector. Okay, so a couple things to notice about kinetic energy. The first thing is increasing the mass or increasing the speed increases kinetic energy just like it does for momentum, just like it does for linear momentum. They're not measuring the same thing because kinetic energy has the speed squared and momentum has the speed as a linear term, but in some sense they're kind of measuring similar things. The biggest difference, though, is that linear momentum is a vector quantity, and so you can talk about the direction of linear momentum. There's no direction for kinetic energy or any kind of energy. So kinetic energy like all forms of energy is a scalar. So energy has no direction. And units for energy. Any form of energy has units of mass times length squared over time squared. And so in SI units, energy is given as kilogram meters squared per second squared. Well, we use energy enough that, and that's a cumbersome enough set of units that we just give it its own name, the same as we did with newtons. And so we call this unit the joule. It's the name of a scientist, and we abbreviate it with a capital J. So any energy, including kinetic energy, has units of joules, and 1 joule is equal to this. Okay, so perfectly elastic collisions satisfy 2 equations. The first one is conservation of linear momentum. So the mass of object 1 times its velocity plus the mass of object 2 times its velocity, as many as you have before the collision, is equal to the same thing after the collision. But then what perfectly elastic collisions have that inelastic collisions don't is that if you add up the kinetic energies of the objects before and after, they have to be the same. So kinetic energy is conserved. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and as many objects as you have before the collision, is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared, as many as you have after the collision. And now that you have these, you just have to solve this as a system of equations to get the velocities that work. Okay, so as an example, let's go back to the kid on the skateboard. And so here's the kid. But this time the ball comes in and hits him right in the face and bounces off. And we're going to assume that kinetic energy is conserved in that collision. And the question is, what are the velocities of these objects after the collision? Immediately after the collision. Okay, so again, we're going to take a top view. The ball's coming in at 10 meters per second. The kid's at rest initially. The mass of the ball is 0.5 kilogram. The mass of the kid is 20 kilograms. And we'll use the same coordinate system we did before. Okay, so conservation of linear momentum. Says the mass of the ball times its velocity before the collision plus the mass of the kid times the kid's velocity before the collision is equal to the combined mass times, we're going to have to assume that all this motion is happening in the same line for this in order to solve it. So we'll write it as Vx0. And from that we get one useful equation that says 5 plus 0 is equal to 20.5. Whoops, erased it. I did that like it's inelastic. Okay, so if it's elastic, then after the collision, we have 0.5 times the velocity of the ball, and we're assuming it's in the x direction. That could be positive or negative, plus the mass of the kid, and we're assuming that that's also horizontal. So we get one useful equation that says 5 plus 0 is equal to 0.5 VB plus 20 VK. Or I'll write it as 0.5 VB plus 20 VK is equal to 5. Okay, so in the inelastic case, we could solve at this point. We had enough equations for the number of variables. This time we don't. We have one equation, two variables. And so we have to go to the other condition that says kinetic energy is conserved. Okay, so yep.
Since the guy's on a skateboard with wheels, there's no friction with the ground.
Right.
Wouldn't the ball hit him and keep going forward? It wouldn't. It doesn't feel logical to me. Like it would just bounce off. Wouldn't it hit him and keep? Wouldn't they both keep moving forward?
Think about it like these things. Think about these things. This desk toy thing.
Yeah.
And actually, let's just think about two of them for now. So the way these work is, so this is even better than no friction, right? It's not even, this is just freely hanging there. When this ball comes in, what's going to happen there is this is going to stop dead, and this one's going to bounce away. So yeah, the reason that happens, I guess you could say, is that there's enough force caused by the inertia of this, running into the inertia of this, to stop this dead. And it's going to be even more dramatic in this case because the ball's a lot lighter than the kid.
Yeah.
So if this ball had less mass than this, then when they hit, if it had just a little bit less mass, this would bounce back just a little bit, and this one would bounce away with a little bit less speed than that one. And if there was a big difference in masses, if this was 100 kilograms and this was 1 gram, this would bounce back basically just like hitting the wall. Hitting a wall, this would barely move at all. Okay, so the requirement that conservation of energy, that kinetic energy is conserved, says before the collision we have 1/2 times the mass of the ball times the speed of the ball squared. That's the kinetic energy of the ball before the collision, plus the kinetic energy of the kid before the collision, which is 1/2 times 20 times speed of 0, so this is going to go away. And that's equal to the sum of the kinetic energies after the collision. So 1/2 times 0.5 times VB squared plus 1/2 times 20 times VK squared. And I'll simplify this a little. If we divide everything by 0.5, let's divide everything by, so we'll cancel out the halves, and then we'll divide everything by 0.5, and you get that VB squared plus 40 VK squared is equal to 100, yes, 100. Okay, so there's our system of equations. Yes?
Shouldn't it be 0.5 VB squared? Because the 0.5 is eliminated, just the half out in front.
I eliminated the halves, and then I divided everything by 0.5 to get rid of the...
Okay.
Okay, so how are we going to solve this? There's one thing, really just one thing you have to, what you don't want to do is try to solve for one of the variables in the square equation, in the kinetic energy equation, and plug it in here. That's unnecessarily complicated. Solve for one of the variables from this equation, and then plug it in here. Okay, so if this is, I'll call this equation 1 and this equation 2 Roman numerals. So equation 1 says VB is equal to 10 minus 40 VK. So VB squared is equal to 100. So let me just write this out. So VB squared is equal to 10 minus 40 VK times 10 minus 40 VK. Multiply that out and you get 100 minus 80 VK plus 1600 VK squared.
Would it just be regular VB instead of VB squared?
What? This, so from equation 1 we got this first one. VB is equal to this stuff.
Oh, okay.
And now we squared both sides. Yep.
Okay, I think it should be 800.
Yeah.
Oh, yeah. Thank you. Okay, so now we can plug that in for VB squared here. And we get 100 minus 800 VK plus 1600 VK squared plus 40 VK squared is equal to 100. Those 100s cancel in this case. And so you get 1600 VK squared minus 760 VK is equal to 0. Is that wrong?
I think it's 1640 VK squared and negative 800 VK.
Ah, thank you. Okay, 1640 VK squared minus 800 VK. You could always solve this by quadratic formula. In a lot of these problems, actually, it's just in the problems where one of the objects has no velocity before the collision. You can just factor it out. So this says VK times 1640 VK minus 800 is equal to 0. And so the roots are VK equal to 0 and VK equal to, what's 800 divided by 1640? 0.49. Okay, those are the two roots. Okay, so there's two solutions here. How do we know which one is the solution that we want? Well, actually, we don't have to do that yet. We've already used conservation of linear momentum, so what we need to do here is recognize that one of the roots is always the object's velocity before the collision, and that's not the one we want. We want the velocity after the collision. So one root is always the velocity before, so you want to reject that one. So VK is equal to 0.49 meters per second. All right, and now we want to figure out VB. To get VB, plug in VK back into the conservation of linear momentum. And we can do it from any one of these. Actually, the easiest one would be, let's use this one here. So VB is equal to 10 minus 40 VK. What's 10 minus 40 VK? Negative 9.6 meters per second. So the ball came in with a positive velocity of 10, and it bounced back almost as fast as it left. It lost a little bit of velocity that it gave to the person on the skateboard. Okay, so intuitively, what do you think? Think about the velocity of the kid. Is that velocity after the collision? So what's going to cause the kid to roll back faster? An inelastic collision where he catches the ball, or an elastic collision where the ball bounces off?
I would say inelastic is the one with 6, right?
So I don't remember what it was.
Inelastic, because all of the ball's momentum is transferred. That's what I'm saying.
So it's actually the opposite of that, but that's a good way to think about it. So what did we get? Where was that?
0.24.
Okay, 0.24. So in the inelastic collision, where the kid catches the ball, the velocity after is 0.24. When it bounces off, the velocity is 0.49. So he's bouncing back faster if he doesn't catch the ball. And the way to think about it is, think about the impulse that the person applies to the ball, the amount of force over time that the kid has to apply to the ball. In the first case, the kid has to slow the ball down to a speed of positive 0.24. In the second case, the kid not only slows the ball down, but he actually reverses the whole direction of the ball from 10 meters per second back to 9.6 meters per second the other way. That's a greater amount of impulse you can think of it as a bigger, like, sort of integral of force. And so that bigger quantity of force is being applied to the kid and sends him bouncing back the other way. But that's always the case. So if you compare an inelastic collision to an elastic collision for the same two objects, the one that continues in the same direction it was going beforehand is going to be, the velocity is going to be bigger for the perfectly elastic case where they bounce. I've heard it said that that's the reason that police use rubber bullets, that because the fact that it's rubber will knock someone down more than, I mean, it seems a little, I think really the reason they use rubber bullets is because it won't kill you as often. But that principle is true. If you hit someone with something that bounces off of them, it sends them reeling back more violently than something that lodges in their body. Okay. Any questions? All right. Office hours at Kennedy today after school.